Welcome to the next video. This is going to be about the mega scale model. Mega meaning a million, comes from Greek meaning great, and it's 1,000 times larger than our previous scale factor, kilo, which was 1 to 1,000. And with 1 to a million, what can we show? The solar system is still a bit too big for there to be anything reasonable. Because the sun is so much bigger than the Earth, the sun is 1.4 million kilometers wide. If you divide that by a million, it's 1.4 kilometers, right? So that's going to be huge, and it's going to be 150 kilometers away, right? So that's still way too big. But the Earth is kind of in the right size where we can look at something interesting. We can draw it out on the beach here. The Earth is 12,800 kilometers wide. Divide that by a million, we get 12.8 meters. So I'll go ahead and I'll draw it out and we'll take a look at it. Okay, so I've used some rope to mark out the circumference of the Earth at a scale of 1 to a million. So how much rope did I need? Here we go. So the Earth in real scale is 40,000 kilometers in circumference, and here we need 40 meters of rope to show the same thing. The diameter is about 12.8 meters at this scale, and we know the Earth has a slight bulge to it, right? It's slightly flattened. The thing, though, is that you can't really tell just looking at the circle, right? So the radius at the equator is about 21 kilometers more than at the North Pole. So assume this is the equator right here, right? So 21, we change that from kilometers to millimeters. It's about that much, right? So this rope is this much further away from the center than at the North Pole. So that bulge is extremely, extremely small. You wouldn't be able to see it with your eye. And what else do we know about the layers of the Earth? Well, we know the crust is about 40 to 50 kilometers wide, right? So that's 40 to 50 millimeters. Let's just do 45 millimeters average, right? So that is about a little more than this width of a stick right here, right? So this is extremely thin, right? For something this big, right? You have an extremely thin crust, almost like an egg. So the planets are, at least the rocky planets, aren't as rocky as we think. They're kind of squishy with a kind of a hard exterior to them, and that's about it. And lying on top of some of that crust is the ocean, right? So the ocean is 4 to 5 kilometers deep on average, right? So I think in the Pacific it's about that depth. So 4 to 5, let's just say 4.5 millimeters here. That is about the width of this little stick lying on top, right? So the Earth has, at least from a distance, it has an extremely shallow ocean, just the thinnest of layer of water that's covering it. And even if we look at the topography of the crust itself, right, we can think of Mount Everest, and so that's almost 9 kilometers, right? So that's almost about 9 millimeters. That's only about this much here, right? So that's going to be this little stone, right? This is Mount Everest, right? As you know, sticking out above mean sea level. Put that right there. And if I move away and think about the context of this whole scale model, it's really nothing, right? You don't get a sense of any topography unless you get very close to the surface and you take a look. Where does the space station fit in with all of this? So at 400 kilometers, space station, let's say on average, is about 400, in this case, millimeters, and the size would be smaller than a tiny grain of sand. It's invisible at this scale, and so you can see that it's extremely close to the Earth. The von Karman line, which is the line where the air basically stops and space begins, is at about 100 kilometers, and that's about right here, 10 centimeters. So this is the thickness of the atmosphere, and everything above this is space. So again, Earth has very thin atmosphere, and within the atmosphere, life can only exist at the very lowest level, right? So the biosphere is just a very thin little layer that extends all along this line. So it's a very, almost like a two-dimensional surface. Now I want to talk about something interesting. 65 million years ago, we had a little accident. We had an asteroid hit the Earth, and this asteroid is really quite small compared to the size of the Earth. It's only this big, right? This is a 15 millimeter marble, right? At this scale, it's about, well, in real scale, it's 10 miles wide, about 16 kilometers. And this little guy comes crashing down on this huge object. And our sense of physics really has to be stretched, because we think, how can such a little marble create so much disaster, right? So at scale level, it's coming in at 10 kilometers per second, right? So it's coming in very slowly, smashing into the Earth, and you would think it would just create a little hole. But of course, as the scale of things change, our understanding of physics is very different, right? So all the mass in that asteroid gets converted into heat, and that heat vaporizes the asteroid, and a large part of the crust gets thrown into the atmosphere, covers the atmosphere in a thick black cloud of dust, destroys plant life to a large degree, and animals die, and that was the end of the dinosaurs. From something that seems very small. So it's surprising how it goes kind of against our intuition of how things operate. And this is something that happens more and more as we deviate from our scale, our natural scale, 1-to-1, of how the world works, right? We have an intuition of how things fall and how they move. And as we get into the very small or the very big, it actually operates very counterintuitively. So this is what happened when the dinosaurs died. So that was 1 to a million. And if we want to bring in some other objects in the universe, like the sun and the moon, we need to go to our next level, which is 1 to a billion. And that's the topic of the next video, which is the giga scale model. See you then.